All right, so in this optional lesson today, we are going to be exploring the conservation of momentum in 2 dimensions. So essentially, we're going to look at 2 scenarios. One, we're going to look at a glancing collision. So when 2 objects collide, not head-on, they collide on maybe not at their center of mass, and when they move apart, they're both moving at an angle. Likewise, another example we're going to look at is an explosion example where you have one initial mass that explodes into multiple pieces. And we are going to assume then in the second example that those pieces would move parallel to the ground, so that would only be a 2-dimensional situation. So 2-dimensional conservation of momentum is the same as the first, and is premised on the fact that the total momentum before a collision equals the total momentum after the collision. So that is the same. That is the law of conservation of momentum. However, what is different is that these objects will be moving in 2 dimensions. And so we have to use our techniques for adding 2D vectors. And I would recommend that we would do the vector component method. Okay, so we'll take a look here as how this is going to work. We'll read the question carefully and then go from there. 2 identical curling stones of mass 19.5 kilograms. They're identical, which means the masses are the same. So MA equals MB. So we'll say the first stone is A, the second stone is B. So the first stone hits the stationary second stone. Stationary means V1B is 0. Therefore, the initial momentum of B is also 0. Very convenient. So the velocity of the first stone, V1A, is 5 meters per second north. After the collision, the velocity of the first stone is 3.2 meters per second, 30 degrees west of north. Find the velocity of the second stone after the collision. So find V2B. So the first thing we're going to have to do is find out the momentum vectors. We need to find P1A, P1B, and we need to find P2A, because P2B is our unknown, the momentum of the second stone after the collision. Technical difficulties here. Okay, so we know that P equals MB. So even if the object's moving in 2 dimensions, we don't have to worry about the angle for the momentum. We can just multiply by the velocity. So P1A will be the mass, 19.5 times 5 meters per second. So the 19.5 kilograms and 5 meters per second. That yields 97.5. 97.5 kilogram meters per second north, because of course it's moving north. P1B, of course, is 0, it's stationary. P2A is going to be 19.5 kilograms times 3.2 meters per second. We'll look at the magnitude only, so that's 62.4 kilogram meters per second, and the angle will be 30 degrees west of north. Okay, so now we have our momentum vectors. It's time to set up the conservation of momentum. So P1 total, the initial total momentum, equals the final total momentum, P2 total. So the momentum comes from 2 objects, A and B. P1A plus P1B equals P2A plus P2B. Now P1B is 0. So P1A equals P2A plus P2B. P2B is our unknown. So P2B would equal P1A minus P2A, or again, if we're adding but subtracting vectors, we add the negative. So P1A plus the opposite of P2A. So now, essentially, we have our method of doing this. Now we could even go further and insert what we know. It would be 5, not 5. P1A we calculated 97.5. I'm just going to leave the units out for right now, and that's north. And we're going to add, okay, now we need the opposite direction. So P2A is 30 degrees west of north, so we'll say 30 degrees south of, 30 degrees west of north. The opposite would be 30 degrees east of south. 62.4. So 62.4, 30 degrees east of south. So now that gives us, okay, a way to set up adding these vectors to get P to B. So we will then set up our XY table. X, Y, and the vector we have P1A negative P2A, and of course what we're getting when we add these is P2B. Okay, so if we look at the X and the Y, the P1A only has a Y component because it's north. So P1A in the X would be 0, and P1Y would be positive 97.5. Negative P2A, so it's 30 degrees east of south, so we can draw a diagram here just to help. So we've got the south, we've got east, so east of south, so it would be like that. So there's our X, and there's our Y. So our Y is adjacent to theta, and our X is opposite. So negative P2A is going to the east, so it would be positive. The X would be 62.4 times sine 30. So it would be positive 62.4 sine 30 because theta is 30. X is the adjacent. X is the opposite side. That's the X component of P2A. The Y component would be 62.4 cos 30, but it's going south, so it'll be negative. So negative 62.4 cos 30. And now we can get our final answer for get the X component for P2B and the Y, and then we'll get our triangle and then our angle afterwards. Okay. So simply, we're going to take 0 plus 62.4 sine 30. So we'll make sure the calculator is in degree mode. (62.4 sine 30). 31.2. So it'll be positive 31.2. So that's going east for the X. Now the Y component would be 97.5 minus 62.4 cos 30. And you get 43.46. Positive 43.46, which means the Y is going north. So this thing is going north of east. Okay, so now our final triangle, we have our x going east, our y going north, and then that would be P2B with our vector, our angle theta. So P2B will equal the square roots. Hopefully you know a squared plus b squared equals c squared. So 31.2 squared plus 43.46 squared. And then the angle will be inverse tan y, which is 43.46 over x, which is 31.2. Okay, this becomes quite repetitive. So 31.2 squared. So bracket 31.2 squared plus 43.46 squared, and then take the square root. Okay, second function, square root of the answer, and you get 53.4996, so 54. Well, we'll take it 53.4996. 53.4996, that's kilograms meters per second, and the inverse tan, .46 divided by 31.2, 54 degrees. So what we would care about then is that our direction, so P2B is 53.4996 kilogram meters per second, 54 degrees north of east, okay, or east 54 degrees north. All right, now, a lot of students would be tempted to stop there. You certainly have done a lot of work, but the question is not asking for the final velocity of the second stone. It is asking for the final velocity of the second stone. We have to do one last thing, and that is find the velocity by dividing by mass. Remember, P equals mv, so V would equal momentum over mass. So the velocity then would equal 53.4996 divided by the mass. Remember, the stones had identical masses, so 19.5. So you would take 53.4996 and divide it by 19.5, and you get 2.7436. 2.7436 meters per second. Now, if we are going to attend to sig figs, okay, we have 2 sig figs as the least number. So our final answer that we would box be the velocity, the final velocity of the second stone, so that's the velocity of the second stone after the collision, would equal 2.7 meters per second. And the direction would be the same as the momentum vector, so that would be 54 degrees north of east, or east 54 degrees north. And that is how you solve a 2-dimensional momentum conservation question, okay, involving 2 objects. So there is a lot going on, okay, but that is how you do it. And that would be example 1. Okay, so we will look at the second example, which is that of an explosion. So typically, we're going to look at an object at rest. So the initial object will always have a momentum of 0 if it's not moving. So we've got this scenario where we've got this object, okay, and it's going to essentially break into 3 pieces, A, B, and C. So it's initially at rest, then it explodes, so each of these pieces are going to move in those directions. Now, that's just an example. I don't think they're moving in actually those directions, but you get the idea. So there would be momentum vectors. So there would be P2B, P2C, and P2A. And so the total momentum, P2, total, obviously would then be the sum of the three momenta. So P2A plus P2B plus P2C. So you add all those together, that would be P2 total. And of course, P2 total must equal P1 total, which is equal to 0. Okay, so that's the premise. Again, it goes back to the fact that P1 total equals P2 total. The total momentum before collision equals the total momentum after the collision. So we're saying that the bomb is at rest, so 0 equals P2 total, which equals P2A plus P2B plus P2C. Okay, so that's kind of the premise that's going on here. We are going to know two of these objects and not the third. That's how it works. So we know the total mass of the bomb, M total equals 5 kilograms. So if it breaks into 3 pieces, the 3 masses must add up to 5. So they travel parallel to the ground, which means 2-dimensional only, not 3D. The first piece is, so MA is 1.2 kilograms. The second piece, 2.5, so MB equals 2.5 kgs. So we need the third piece. We don't know, so we'd have to figure it out. So let's take care of that first. We would take 5 minus 1.2 minus 2.5, and you get 1.3. So the third piece is 1.3 kilograms. So that's important to note, okay? So we have 3 pieces, A, B, C. They add up to the total. All right, so what velocities do we know? We know the first velocity, the velocity of A after the explosion, 5.5 meters per second. We know the second one for B, 4.1 meters per second. We want to find the final velocity of the third piece. So the unknown is V2C. To get V2C, we need the final momentum of C. So essentially, we're solving for P2C. So if this is 0, then P2C, okay, would equal, we have to move these both to the left. So if we added these up, we'll put a bracket here, we would add them, So it would be negative P2A plus P2B. So a little trick here. All we really need to do then is add these two vectors for momentum A and B, and then take the opposite direction. Okay, so we can add P2A plus P2B. It's going to be X and Y and all that, and then we'll get P2C, and then we just take the negative because, of course, it is negative because of the equation. But before we do that, we need to find the two momentum vectors, P2A, P2B. Again, P equals MV, P2A will equal MA times V2A, and P2B will equal MB times V2B. We can plug and chug on that. We know MA, we know MB. So the first calculation then will be MA 1.2 times the velocity of the first piece, which is 5.5 meters per second. And we get 6.6. So P2A is 6.6 kilogram meters per second, and the direction is the same as the velocity, so 20 degrees south of east. P2B, the mass of B is 2.5 kilograms, and the velocity is 4.1. 2.5 times 4.1 gives us 10.25. 10.25 kilogram meters per second. Our direction is the same as V2B, which is 25 degrees north of east. 5 degrees north of east. Okay, so we know P2B, we know P2A. All we have to do now is add the two. P2A, P2B, add them with vector components, and then get the final triangle, a squared plus b squared equals c squared, inverse tan, and then get the opposite direction for the actual final momentum of the third piece. So we can set up our XY chart. X, Y, we've got P2A, P2B, and we are going to be solving for P2C. And again, we want to get the negative direction, so make sure that we get the negative, the opposite. Okay. So, based on our directions, hopefully I'm not going to draw the triangle so you're comfortable. 20 degrees south of east. We're measuring from the angle of from the x. So x's cosine is y. So south, east. So east means positive. So the x component would be 6.6 cos 20. And the y component would be negative 6.6 sine 20. Because, of course, it's south of east. For P2B, it's north of east. Again, it's off of the x-axis. Okay, north of east. So x is adjacent, y is opposite. So it would be both positive for x, positive for y. X and y are both positive. So 10.25 cos 20 and positive 10.25 sine 20. Okay, so now all we have to do is plug and chug. So we're going to add these two x's and y's to get the P2C. So for the x component, 6.6 cos 20 plus 10.25 cos 25. I think it was, whoops, that should be 25. Did I write that wrong? 25. Cos 25 for the B, sine 25 for the B. My apologies. So 6.6 cos 20 plus 10.25 cos 25 gives us 15.4916. 15.4916. Now, it ends up being positive, so we'll deal that out. Okay, so now we will take the y component. So negative 6.6 sine 20 plus 10.25 sine 25. And that gives us 2.0745. Positive. So positive 2.0745. And we've got positive 15.496, which means the P2C right now from our sum, it's going east and it's going north. Okay, so we'll draw a triangle. It's going x and y, east, north, theta, and then there's P2C. Notice I'm not putting the negative because we want to find the negative. We'll do that after. So x, y. So P2C, okay, a squared plus b squared equals c squared. So 15.4916 squared plus 2.0745 squared. And then we'll do our inverse tan afterwards. So inverse tan x, inverse tan opposite over adjacent, so the y, 2.045 divided by 15.4916. So 2.0745 divided by 15.4916, and we'll get our angle. Okay, so we'll go and plug and chug this. 15.4916 15.4916 squared plus 2.0745 squared. And then we take the square root of the answer, 15.62988. 15.62988 kilogram meters per second. And our inverse tan, 2.0745 divided by 15.4916 gives us 7.6. We'll take 8 degrees. And this is 8 degrees north of east. So P2C is 15.62988 kilogram meters per second, east, 8 degrees north. So we want the negative P2C. That's going to be 15.62988 kilogram meters per second, west, 8 degrees south. Very, very important what we just did there. Okay, now we don't want the final momentum of the third piece, we want the final velocity. So again, we go to the fact that V equals P over M. So V2C will equal 15.62988 divided by the mass of the third piece, way back at the top, which was 1.3 kilograms. And we will get our answer. So 15.62988 divided by 1.3 kilograms gives us 12.02 per second. With 10 to sig figs, I believe we need 2 sig figs, so 12. So finally, the velocity of the third piece C after the collision, so V2C, sorry, after the explosion, V2C would equal 12 meters per second, west, 8 degrees south. That would be the direct way to solve for an unknown velocity again from an explosion type example. So this is a busy one because there's 3 masses, but if you follow through what we did, take your time with it, it should come together. There are some practice examples here. Again, this is optional. Okay, I will not be assessing you formally on this for our remote learning for this semester.